So please.
Yeah. Thank you, Alessandro. Thank you for giving me the opportunity to present my work here. And thank you for everyone coming for this early session. So I will tell you today about our joint work with a bunch of people, mainly Shlomo Razamat, but also there was his student involved in this project, Bilal Nazar, and lately we were working with Hichol Kim. The project is going for some long time. My goal here is to give you some overview basically and give you basic ideas. I will try not to go much into technical details, so sometimes I will be simplifying things. So what is it about? It's about, generally speaking, it's about the topic which is one of the main topics of this workshop. It's about emergence of certain mathematical integrable structures in different supersymmetric field theories when we consider some of their observables. And more particularly, as follows from the name, what we'll be considering here are n=1 superconformal indices. So let me just write indices. With introduction of surface defects. Okay, because people live in different dimensions here, we are in 4D, of course, so this is 4D. This is on one side, and on the other side, I will show how elliptic finite difference operators basically emerge. So, and these operators, in many settings, they're shown to be integrable. In other settings, we conjecture them to be integrable. And this should be studied. The prototypical example of this correspondence was proposed actually already quite a long time ago by a bunch of authors, including Shlomo. And prototypical example is class S theories on one side. So, which are n=2 theories, not n=1 as I wrote here. And on the other side, they were obtaining Ruhin-Nars-Schneider model, which is nice integrable model, which appears in physics quite a lot. So this is from 2012. Since then, there were a couple of other theories in 4D considered. For example, class SK, also by Shlomo together with David Gayotto. But then not too much was done. But recently there was quite a progress about understanding compactifications of others. Yeah, it's crucial that we will have compactification. I will come to this in a moment. So there was better understanding of compactifications from 6D superconformal field theories, and a plethora of such compactifications down to 4D were derived. So our initial goal in this project was to analyze this compactification and understand what's going on right-hand side of this correspondence. So, okay, this is a bird view of what we were doing. Now, let me go to a particular setting. As I told you a moment ago, we always start with some 6D superconformal field theory of your choice. In this case, it was the favorite one, of course, 2,0, but it can be others, and I will tell you much later which others they are. So, so this is our UV basically. Then you put this thing on some Riemann surface with some punctures, and you can put flux for the global symmetry on this Riemann surface, and this initiates RG flow across dimensions. We arrive to some 4D IR QFT, and that's the QFT we will be studying. Of course, as you know, sometimes it happens that there is another 4D UV point UV fixed point of RG flow, which can be deformed by some relevant or marginally relevant deformation most often, so that it flows to this IR QFT, and in this case, this QFT has Lagrangian. But that's not always the case. I will be specifying when we need Lagrangian and when we don't in our construction. Okay, and of course, all this depends on that. So this is our Riemann surface C of genus G with some number of punctures. Of course, all this, both IR fixed point and if 4D, IR QFT and 4D fixed point, if it exists, it bears the information about compactification. So which theory we started with and where we compactified. Okay. So this is our setting. For our construction, it's crucial we start with 6D. So if you take arbitrary 4D n equal 1, you most probably won't be successful. Okay, so this is general setting. I will reserve this space for first 20 minutes of the talk for the pictures I prepared. So I will be erasing often. Okay, I hope you remember the name of the talk. So, right, this is our setting of theories we consider. Now, let me tell a couple of words about the observable in case you forgot or never saw indices. Okay, so what we consider is superconformal index, which I will refer to index for shortness. And this is the following observable. I will explain what it depends on. So in supersymmetric QFT, so first it was introduced for superconformal field theories, but in principle you can define it for supersymmetric field theories as well. Okay, I ran out of space here. Okay, so what is what in this index? So basically we put our theory on S3 cross S1, and we do radial quantization on S3, actually on S3 cross R, and then we compactify R to S1. We do radial quantization on S3, and we compute the trace over basically BPS states of theory quantized on S3. It's a sort of generalization of Witten index. So, and then what are these variables, which in fact index depends on? These are fugacities, which helps us to keep track. This is bookkeeping mechanism for keeping track which BPS operators, so BPS states and quantization, are charged under which symmetries. So symmetries here are, so the isometries of S3, which is spin 4, and this corresponds, so this has charges G1, G2. So then there is R symmetry with charge R. So everything stands in powers, and then we have some global symmetry. Theory can have some global symmetries. So this QI, I called it G4D. This is our global symmetry in 4 dimensions. And so just global symmetry. And charges are QI. So we basically put together some charges, and we enumerate in this way the states of our BPS states of our theory. So it counts short multiplets in theory, and it's very useful. It was used a lot to prove dualities, not prove maybe, but give evidence of dualities. Let's call it like that. And we will be using it for our construction today, because that's exactly the observable for which the elliptic integrable models will appear. Okay, this was last thing for preliminaries is about compactifications. So what do we need to know about compactification? So the most important thing I want to give you, of course I won't give a lecture about compactification of 6D series, it's a different topic, but what we need for our construction is to understand what the puncture is. And we take simplified picture of the puncture. If you were in this business, you of course know that there is quite complicated classification. For us, puncture is just equals the pair of things. So puncture always for us comes with some global symmetry. And set of operators, special operators on the Higgs branch of the 4D theory, which we call moment maps, but this is actually bad use of notations because it's not really moment maps for anything in mathematical sense. There is no some geometric construction behind it. Only in the case of 2, 0 it is, but we're considering more general settings, so it's not really a moment map. So, right. So that's what the puncture is for us. How you can understand it, basically you can consider puncture as tube compactification of your 6D theory. So imagine that whenever you have a puncture, yes.
They're not valued yet joint of GP in any sense, or
they are charged under. They are charged under GP. Yes. Sorry. Yeah, I didn't tell it. They are charged under subgroups, which are in GP, but they are not necessarily in a joint. So it depends on the setting.
Okay.
So good. You can, when this picture is valid in principle, this simplified picture, it's not always valid for any punctures, or sorry, not any punctures, any theories. So we can consider puncture, whenever you have puncture on your surface, you can imagine that you attach tube to this puncture. And that's why puncture can be seen as a tube compactification of your 6D theory. And if this tube compactification have Lagrangian description in terms of some gauge theory, then you put boundary conditions on this tube, and your gauge symmetry freezes and leads to this. And if you put Neumann, directly boundary conditions. If you put Neumann, these operators pop up. So it's sort of real conditions are more complicated. Boundary conditions when you put, so both of them pop up. And that's how we characterize punctures. And there are two operations on punctures which you can do, which we will be doing. So first is gluing. Yeah, what happens when you introduce puncture for the index? Pretty much nothing, because what you introduce is extra global symmetry, meaning that you should introduce corresponding fugacities here, which counts how your BPS states or operators are charged under this global symmetry. So, and there are two operations. So one is gluing. When we take two manifolds, two Riemann surfaces, with a puncture of the same type. So, like I draw here two tori with punctures, with one puncture. And we can just glue these two tori along these punctures, so we get two tori in the end. So fluxes, for simplicity, I will say that they add up. In principle, there are two ways of gluing, called S gluing and phi gluing, and fluxes can also be subtracted, depending on which one you choose. So, okay, and also you need to identify, of course, what do you need to do to do this at the level of the 4D theory? So, at the level of 4D theory, you need to do two things. First, identify moment maps. On two sides of the on two Riemann on these two punctures. So, and practically this is usually done by introducing superpotential coupling these moment map operators. And second, you need to, so as I told you, puncture comes with a global symmetry. What happens when we glue them? We basically gauge this global symmetry. So then you need to gauge GP. So that's what you're doing. Okay. Pretty simple operations. So what happens with the index? What happens with the index? So index, right, I didn't tell you, but this is the form of the index as it's defined. But practically to do calculations, you can use your favorite methods. In 4D, you can compute index in free UV theory, and index is RG invariant, or you can use localization. Localization is nice because it also works for indices in other dimensions, while the method of counting free states in UV free theory doesn't. But one way or another, you land on some multidimensional integral, and then you can compute it. So, okay, what happens with the indices when we do this gluing? Imagine we have index for theory on one Riemann surface, for 4D theory obtained in compactification on one Riemann surface, and on another Riemann surface. So let's call it C1 and C2. And this is C1 plus C2. So, right. And imagine we want to compute index, so it depends on P and Q always. And we want to compute index on C1 plus C2. With fluxes also at the top. So what we need to do, first of all, we need to take two contributions of two separate indices corresponding to compactifications on each of these Riemann surfaces. Okay. So then we need, oh yeah, sorry, let me also, okay. Let me also write, let me write shorter, I1 of x, I2 of x. So I1, I2 are two indices on two Riemann surfaces, and x is fugacity associated with this puncture. So as I told you, each time we have fugacity, each time we have puncture, we associate fugacity with it. So what we need to gauge it, and gauging in this case corresponds to integrating basically over all the fugacities, corresponding to the puncture, and adding some appropriate weight. This weight includes harm measure because you integrate over some group basically. But it also includes the contribution of some multiplets you need to add in order to do this gauging. It's of course vector multiplet, but sometimes you need to add some hyper multiplets as well. So it's pretty well defined operation. So, and this measure is always known. It's not a problem, but it differs case by case. Yeah, but because you need also to introduce this, so it affects charges. So superpotential does not affect index itself, expression for the index, but it fixes charges. So that's what happens. Let me think. No, I mean it should work for S3 crosses one partition function as well. Yeah. It's just because everything I did here is gauging and adding certain multiplets which you need to add. It's not only for the index. With partition functions, maybe you need to be more accurate with superpotential indeed, as as Pietro noticed, because there they can contribute maybe, but in index they don't contribute directly, only through charges specification. So, but in principle it's pretty general statement. Well, I guess it's index plus Casimir basically. Yeah. Ah, yeah, right. Yeah, sorry. If it's S3 cross S1, yeah, it doesn't depend. Yeah. Good. So, right. And second operation, and I'm done with everything we need, and then I will go further fast through the construction. So, and then we can close puncture. So imagine we have puncture and we want to get rid of it. So what does it mean? We need basically, we start with some global symmetry and we need to break it somehow, right? How do we usually break symmetry? We are giving VF to something that is charged under the symmetry, and we have very nice already given set of operators charged under the symmetry. So what we give VF to, okay, you were expecting probably to see M here directly, but I gave VF to something more complicated. So we give VF to this combination. So we also include derivatives. 1, 2, 3, 4 is basically our 4 special dimensions. Why do I do this? Because when I do this, when K and L and or L are non-zero, this corresponds to introducing defects. So, and you can understand it because we introduce VF, which is space-time dependent. This is a bit hand-wavy argument. In principle, you should show in case by case which exactly defect you introduce, and this is much more complicated. But the general statement is that whenever we give VF with derivatives, we introduce some sort of surface defect. Okay. It is wrapping S1, yes. So one direction indeed wraps S1. Okay, we introduce defect. Right, and what do we do with the index? That's a little bit complicated. I will just give you the recipe. Proving it is a bit complicated thing. Imagine M contributes to the index as with a weight some, I don't know, M star times U powers minus 1, and this is some U1 fugacity. This is the fugacity of, yeah, sorry, I went small there. This is the fugacity of the symmetry we want to break. Let's say it's U1 for simplicity, because U1 will always break completely. Okay. So then what we need to, so then from the point of view of 4D theory, we start with some UV point, and we, by giving VF to M or to its derivatives, doesn't matter, we initiate RG flow down to IR. And the statement that our index in IR will be given by residue of this U fugacity in M star of our index in UV. So this is the recipe of how to introduce VEFs at the level of the index, but only if you introduce VEF for the operators on the Higgs branch. In this case, you hit the pole of the index, and computing the residue there corresponds to flowing to giving VEF basically to the corresponding operator. So this is the recipe of what you do to close the puncture to give VEF more generally from the point of view of the index. Okay, now we have, are there any questions up to here? This was like giving you basics in order to understand construction, which now will be very fast because all the components are prepared. Are there questions about components? Okay. Then let me go to the construction, which I already prepared here before the talk to save some time, not to draw pictures. So, how do we construct operator? There is pretty straightforward algorithm. For this algorithm, you need to, okay, let's consider theory that we obtained on some arbitrary compactification on a Riemann surface with genus G and S punctures and some flux, but it has to have at least one puncture of some type, at least one. It can have more. So I drawn this surface here, just some arbitrary surface. We don't care what it is. Second step and second ingredient we need to build it is Trinian theory. So, which, let me refer to T, I don't know, XUV. So this is the theory with 3 punctures. And for our convenience, we want at least one puncture, which I denoted, let me denote it Z here. So, which I denoted with a cross here, is minimal puncture. So what's minimal puncture? It's puncture of rank 1, with a global symmetry of rank 1. So it's either SU2 or U1. We don't necessarily need it, but the advantage of minimal puncture is that if we close it, we always close it completely, because the whole symmetry is broken. Because if you have punctures of higher symmetries, higher rank symmetries, you can break them partially. So you can break their symmetry only partially, and that's not what we want. We want to close it completely. So Trinian is basically this compactification on 3 punctures here with some flux. A flux can also be there. What is important that it needs to be Lagrangian. So it needs to have Lagrangian description. Because if it doesn't, construction won't work. Okay. So, and now we glue these two together. So when we glue them together, what we obtain? We obtain, again, the surface of the Riemann surface of almost the same form with the same type of puncture. So we want on this Trinian to have two punctures of the same type. For this to work, we also have this minimal puncture Z, and our flux now is the sum of the 2 fluxes. Okay, and last step, okay, let me write it here. We need to close Z puncture. So close Z. So if we close this Z puncture, we arrive to exactly the same Riemann surface we started with only the flux shifted. Though flux shifted is an important thing, but the statement is it always can be chosen such that this total shift, so yeah, by the way, closing puncture will give you extra shift of the flux. So there will be extra delta A. So the claim is that we can always, be constructed. So we can always construct such a Trinian that the flux of the Trinian with one puncture closed equals 0. In this case, there is no extra shift, so this thing goes away, and we arrive exactly where we started with. The difference is, though, how we close the puncture. And if we close the puncture introducing the defect, it's not exactly what we started with. It will be what we started with plus a defect. Okay, and after all this construction, if you do all these manipulations, I draw it for Riemann surfaces, but of course, you need to do it for the index. So if you do all these manipulations at the level of the index, you flow to some IR theory. Okay, I will put indexes k and l according to the number of derivatives we give of moment map operators we give VEF to. So these indices will have, it's a family of indices, and they are proportional up to some factors to certain finite difference operators acting on the fugacity in UV index, on the fugacity U, which was corresponding to the fugacity of the puncture we glued our trinion to. So we have some puncture. We act on the fugacity of this puncture with some operator. So this is family of elliptic operators, finite difference operators. We act on it, and in this way, we obtain the index of a theory with a defect introduced. So it's a pretty nasty way to go, but we get the result. So, and in some cases, you can reproduce this result actually in more direct calculations. Like there was calculation of, again in class S theories, of introducing Gukov-Witten type defects into 4D theory directly, localizing it and looking on this surface, putting some sigma model on this surface, and the result was exactly the same in that as this one. So direct calculation in this case it supported this result, but in other settings there were no direct calculations. In fact. Okay, that's how operators are constructed. Any questions here?
Is the paper that by Shlomo and Rastelli?
Basically, yes. Well, okay, Shlomo and Rastelli did this. The paper where they compared it against Gukov-Witten is Gade and Gukov. Yeah, sorry, I'm not giving my references here, but not to write on the blackboard, you know, all the surnames. But if you want references, you can ask.
Yeah, sorry, can you give some examples of this OKL?
I'm going there, of course. You are jumping exactly 1 minute ahead. So, okay, and exactly as Yegor asks, examples. So basically, examples are results of our work. Well, first example, you start with 6D 2,0. You put it on a Riemann surface. You have 4D class S here. So, okay, and the resulting thing is Ruchener-Schneider, which for rank 1 is given by, in rank 1 there is only one operator, one independent operator. Of course, you get all operators with K and L, but the question is which of them are independent. So in case of Ruchener-Schneider, it has this form. So, okay, let me write that it acts on some function. Q half x plus x to x minus 1. So, okay, this is what Yegor knows very well, of course. In a minute, actually, I will tell you also why it's useful. Because it's not done, you know, just to derive these operators. This is one nice way, because you have the way to generate some, as I will discuss later, a bit later, integrable operators. But actually, it's not only for this, it's to do some real calculations in field theory as well. Okay, this is one example, and this is exactly, okay, let me say Gayota et al. In 12. Right, so,
Sorry, so this works for
Not only rank 1. Rank 1 I just gave rank 1 operator, but this formula, yes. Yeah, if you no, not any surface. You need to have puncture because this is the fugacity of the puncture. You need to have at least one puncture, but yeah, as soon as you have puncture, this works. Not this works. This works. So right, but we moved it. We pushed it further in our works and gave a couple of other examples. A more exotic one, though. Exotic results are, in principle, interesting, but usually more messy. So you can start from another theory, from E-string theory in 6D. This is basically world-volume theory of M5 brane on D4 singularity. In this case, so here, in order to derive it, you knew trinion, which was just trifundamental. I don't know how to draw quiver for trifundamental. I don't think it's possible. Here, you land on some 4D n equal 1. There is no name for this kind of series. But trinion is known. Trinion was found relatively recently, like in 18 or 19. So it's for E-string, it's SU3 QCD.
One more question.
Yeah.
Regarding this one. Are there cases possible where you get an eigenstate of this elliptic operator?
I'm going there.
So this case is not like that. This is some generics.
Sorry.
This can be rewritten as an eigenstate. The one you were just.
It's more complicated, a little bit more complicated. In 5 minutes, just patience. Yeah. It's not eigenstate, but it's related. That's in fact why I have Spectra in the name of the talk, because we have something to say there as well. So okay, it's SU3 n equal 1 as QCD in the middle of conformal window. So SU3 with 6 flavors. Why I drawn it like that? It's because each of these nodes of global symmetry corresponds to 3 punctures. So we have 3 SU2 punctures, and I split the global symmetry so that punctures are visible. And there are 8 moment maps for each of the puncture. Okay, and what do we get on the operator side? We get another operator which is known. It's Van Dien model, BC1. BC1 Van Dien model. It's certain generalization of it is certain generalization of Ruchiner-Schneider, and in case of BC1, which is E-string case, this corresponds to the following operator. So it's also sort of looks like Van Dien, but like Ruchiner-Schneider. I think it's x squared here. So theta are theta functions, of course. Oh, okay. Let me erase this. Psi of qx. Okay. Okay, there is also some constant part. So we have this shift part. There is constant part, which is elliptic meromorphic function with certain poles. Like poles are located at x 1/2 and x equals the same, but with p, I think. Doesn't really matter. The particular form of this function can be different. The most important is location of the poles. So, okay, and this operator is due to Van Dien, of course, from 94, and it's known to be integrable. So we obtained yet another model. Also, Babak with his collaborators obtained it in a slightly different way from Zyberg-Witten curve, which is interesting. Yeah, because it's two ways of obtaining operators in the same operator in slightly different setting. So they were not relying on some index calculation. But yes, this is one of our results. And we went further. So this thing has E-string, has higher rank generalization. One is rank Q E-string that we didn't manage to do because there is no known Lagrangian description for the Trinian compactification. In general, Trinian is not known. It's not that it's not non-Lagrangian. It's not known. So, but there is another high rank high rank.
How the knowledge of the Trinian enters in the construction of because you said it's necessary you have the Lagrangian.
Yeah, because you need to write index for it. Because in the end you need to do calculation. Notice this I didn't care about. This Riemann surface I didn't care about at all. To derive operator you need Trinian basically. That's the most important. And you need to write index precisely and compute some residues. If you don't have Lagrangian.
So computing those residues you get those.
Yes, exactly. Yeah. Computing residues, I see that there is some operator acting on this fugacity. Yeah, because residues they make shifts of the variables. So, but it's complicated calculations. It's super long and complicated. It's hard. I gave you idea of how it's done because to show it, it's impossible. Basically, it's very long. Okay, right. And we went further. There is another. So there is the n+3 conformal matter theory, another sort of high rank generalization of E-string. This is single M5 brane on the n+3 singularity. Okay, and here Trinian is also known. It's also SQCD in the middle of conformal window, but this time of rank n+2. So, and in this case, we also did some operators. I won't write it. They're very scary. You can find them in our papers. Operators start being a bit ugly. But the thing I want to mention is that this, when compactified down to 4D, has three types of punctures. So AN, CN, and A1 powers N. Okay, so there are three types of punctures according to the global symmetry they have. And hence you have different types of, yeah, sorry, I didn't mention actually here with Van Dien. What is this HI? You have eight parameters HI in Van Dien. And if you remember, I mentioned it super briefly. Each of this each of the punctures have 8 moment maps. So these are precisely charges of moment maps. Yeah, that's, I forgot to mention, and nobody asked me what is HI. So, okay, now you have like, in deconformal matter compactifications, you have these three types of punctures, and each type of puncture should correspond to separate type of operators. So, because the operators are acting on the punctures, and of course they should respect the symmetry of the root lattice. So, these are different operators. So, what we did, we derive operators for this. For this, we managed to derive operators for C2. So C1 is basically there. And this we didn't even try to approach because this is too complicated system. So, okay, that's what basically we did in our papers. If you want particular operators, you can look there. Okay. I'm finished with this part, and last 15 minutes I want to talk about eigenfunctions and so on. But are there any questions at the moment? Yeah, so, yeah. So, Schur index is the limit of the usual index, basically. Yeah, of course. So you can go to McDonald's limit first. Sure is too simple. But you can go to McDonald's, and there is sort of McDonald's limit here. It's called Kurn-Winder limit, but it's not studied at all from the point of view of physics. So it's actually, you see, this is why also these computations are useful. If you are given n equal 1 index, it will be very hard to tell which limits to consider in order to get something interesting. But once we get this operator, we already know that there is analog of McDonald's limit, for example, for these operators, which reduces them so that the eigenfunctions are known in terms of polynomials. So, and hence, in principle, we can study corresponding limits on the index side, but we didn't do it yet. But in principle, yes, something like that can pop up. This is actually why we're doing it. This is one of motivation from physics point of view. Any other questions? So, okay, now let me go to the spectra. So there are two properties of these operators, which comes from 4D S-duality, and it can be also proven by this kind of pictures. I won't prove it because of the lack of time, but I will just mention them. First property, all these operators. So we have towers of operators. All these operators commute with each other. Okay, and this is why we basically conjecture integrability. Of course, it should be shown that how many of them are independent, dependent, so integrability is more complicated, but this is a big hint. This and the fact that two of the models obtained are known to be integrable. So let me write here integrability with a question mark. So, okay, this is one property, and the second property is the following, that 4D n equal 1 indices are kernel functions of these operators O. Okay, what is kernel function? Let me explain. So imagine you have index corresponding to the compactification on a Riemann surface with two punctures. These two punctures can be of different type or of the same type, doesn't matter. So, and this index is so E. So let me schematically give it two variables corresponding to two punctures. So, and we can act on one puncture, and the result will be exactly the same as acting with operator, maybe of different type even. Actually, we have proven, it follows from construction, but we have obtained operators, and we made a calculation directly, cross-checking that it works, even in the case of operators being of different type. For example, C2 and A3. So, and A2, sorry, yeah. They can have even different symmetries, the punctures. But okay, this is the kernel property, so that basically all indices are kernel functions. So they are not eigenfunctions, as Babak suggested. They are kernel functions. But how is it useful? It's useful in a way that for kernel functions, the natural ansatz, let me write it for again, index of theory with two corresponding to compactification with two punctures. So, is sorry? That's a good question.
You can bring OB to the left-hand side and the inverse.
Yeah, but this will be different operator.
It's composed of them.
Yeah, it's composed of them. I think they're invertible, but the problem is it will be different operator. Yeah. So, Okay, actually, let me take trinion here. So let me ABC.
In the case of the foundation model, this O operators, they included this W, right? This last piece.
Yeah. Yeah.
Are inside.
Yeah. Of course, yeah. Actually, that's the case where we checked it by direct computation, despite it follows from construction. No, just to be sure. Okay, the following concept makes sense, is natural. So, and one can check that it works. Okay, where psi alpha are eigenfunctions of our operator. I don't know, which we don't know. So these are eigenfunctions. So the point is that this expansion is diagonal, meaning that you don't need to put different indices here and sum over all of them. You expand in diagonal expansion. And moreover, this coefficient C alpha is fixed also. It's given by the inverse of the residue of psi alpha at certain point. So hence we completely fix the index in terms of eigenfunctions of these operators. So in this case, the index of the trinion. And in fact, this can be showing by basically imposing consistency condition on this expansion. You basically should take two trinions, glue them together along one of the punctures. In the end, you get four punctured sphere. And then you can close one of the punctures. And this equals to back three punctured sphere. So doing these operations with this expression and checking the consistency that you end up with the correct trinion which you started with leads to this expression. So that's how you get it. Okay, good. And this is already a strong result because now you can compute indices even for non-Lagrangian theories, provided you know the eigenfunctions. So even if the theory is non-Lagrangian, in this case it's trinion, we know it, but some other theories are non-Lagrangian, and we can use this expansion and bam, we are done. Though there are no other ways to compute non-Lagrangian indices of non-Lagrangian theories. So, and it was used in order to compute indices of class S, but in Macdonald limit. So, because the eigenfunctions of Ruchiner-Schneider in full elliptic case are not known, they are known in Macdonald limit or Schur limit, which was mentioned. So, okay, but now what we did. So this was known. Okay. Yeah. Now. Well, yeah, exact are not there to. Yeah, right. But the point. Yeah. No, but these are just basically these ramified instantons with non-perturbative completion. Yeah, that's what for Yegor. This is for Yegor, the answer. And that's what we check with Hitchell. We check our eigenfunctions, which I will tell you about now, against these eigenfunctions. But they're exact in the sense that, realistically, you do calculations up to certain order in instanton parameter because you can, yeah. Expression, yes, but to compute it really, to put it in Mathematica, you go up to certain order because not very far. Yeah, okay, yeah. In this sense, I will give you now explicit expression as well. Okay, well, what? Yeah, you see, if I want to Right. Yes, but what I want to say is the following. Macdonald limit, yes. But imagine I'm computing index and I want to compute spectrum of the operators. For this, I need to do certain expansion. And that's what we were doing with Hitchell. And we didn't manage to go very far. because it's really this ramified instanton calculation is pretty complicated. It's like closed form expression, but doing real expansions is a bit. But yeah, I agree with you. Yes, I agree with you that now the functions are known, but I'm not sure that they're super useful for computations of the index, though. That's my claim. Okay.
One more question. Are these related, these psi's, to defects in some sense? That you insert at these functions?
Well, related. You mean?
Are they defect partition functions?
It's from 5D point. Yeah, from this, yes, but the. In
completely different set.
Yes, that's what I wanted to say. But for Babak, no, this is setting in 5D where there are eigenfunctions.
In some sense. Hey, but that would be interesting.
That I think they are dual because there is a Calabi-Yau here behind us. But that can be cured. I will look it up.
Okay.
Okay.
That would be very interesting.
Okay, since.
It is a bit fuzzy, Yeah.
Okay, since I'm running out of time, let me give you my last word about the alternative for approach with ramified instantons, which is a bit involved, but okay. It's also computationally difficult, so we hoped we can find something computationally easier than computing these ramified instantons. In the end, we found the algorithm of the same complexity in terms of computing expansions. So, okay, just give me 5 minutes. So let's start with two-punctured torus. We start with two-punctured torus. And corresponding index can be written according to this. So alpha of u, psi alpha of v, with some coefficient c alpha. So alphas, in case of A1 Ruchiner-Schneider, for example, these alphas are numbers, but of course you have partitions in general. These alphas can be complicated indices. So then there is a conjecture which is physically motivated, and our idea is that we cross-check this conjecture in the end. Is that C alpha? So C alpha. So imagine we are considering things. So let's introduce this parameter x equals pq, and imagine that. So since we are always in the regime where p and q are inside of a unit circle, so hence also x is inside the unit circle. And let's say we conjecture the following, that this C alpha are of order x to the powers n alpha, with an alpha 1 bigger than an alpha 2, if alpha 1 bigger than alpha 2, actually greater or equal. So basically we say that these coefficients C alpha are growing, has growing orders with x, non-decreasing orders with x, when we go to higher and higher eigenfunctions. So, right, assuming this, let's start gluing together such tori. So just take two tori, glue together, 3, 4, 5, and so on. In the end, we glue together n tori, and the index of the corresponding index in this case will have the following expansion, as can be shown. Okay, now, since we're inside the unit circle here, so this x parameter is smaller than 1, we can take it even small. So we have here large power of n. Let's take this power of n to infinity. What will happen is that the only contributing term then will be the ground state term because of this conjecture. So, and from here, so basically I limit n to infinity in equals, so goes to C0 powers n psi 0 of u, psi 0 of v. So if we glue infinite number of tori, basically. So from here, we can compute C0 pretty easily. So we compute C0 as limit n to infinity, sorry, in plus 1 in. Actually, they both depend on u and v, but this dependence drops when we take this ratio. Okay, this computes C0. And then back from there, we can compute also the ground state wave function in the following form. So this is also limit, sorry. This is also limit n to infinity. So in practice, so of course here you need to take this n to infinity limits, which is complicated because that means that you need to write index of infinite number of torus glued. So this is of course not realistic. Realistically, we do the following. We want to see the expansion of these eigenfunctions and these C0 coefficients in terms of this variable x. And this is natural for index. That's what people usually do when they compute the spectra of the theories. They expand index in this parameter. So we expand in this parameter, and up to certain order, in order for this thing to work up to certain order, we need to take certain n here. So we need to glue large enough number of tori together in order to obtain right expansion of these two objects up to certain order in X. That's what we do, and we did it and obtained some eigenfunctions. Unfortunately, only ground state and first excited state in case of Ruchiner-Schneider, but we also did some things for the ground state of Van Diechen and ground state of some other more exotic models which we obtained, which I didn't mention here. And in our last work with Hichol, which will come up like next week, hopefully, we do exactly what Alba mentioned. There is another approach using ramified instantons. We compare these two approaches against each other, and we match them basically up to certain comments, which I can discuss if you want, but I ran out of time already by 4 minutes. So thank you for attention. And yes.
When you compute explicitly this eigenfunction, you find that you have some absolute power of non-perturbative correction to the original class of Schafer-Schweding.
Yeah.
Can you see that from the index?
No, we don't see it from the index, so we mesh with a B model, where you don't have non-perturbative approach. No,
if I take this elliptic integral system, what is H bar?
it's H bar. Let me think. Just remember. Yeah, it's basically Q. Yeah.
So is the index well defined for Q? So it's like H bar is e to the I. No, Q is e to the I H bar.
Yes, and we need to take it to 1, and index is yeah. We are working here.
Yes, but you see, if you claim that the eigenfunctions are given by this index, this means that the eigenfunctions of your system are not defined for H bar real.
Yes.
We know it's not true, and the elliptic integral system are well defined
Right.
for every value of H bar. And this is where you see
Right, but H bar real is exactly B model. That's what in Antonio's paper is written. No?
No, H bar real, if you have an elliptic integral system, you have momentum on position. H bar is
right, of course, but that's what but that's what they're calling in Antonio's and, okay, I don't know, in Antonio's and others' paper, that's what they call B model and H model, an A model. In B model, they say we take H bar real, and then they have quantization, which doesn't, okay, explain.
A and B model are just two different
Yeah.
depend on the axis on the real line of the function.
Yeah. Okay, so it's
In the B model where you have eigenfunction,
yeah.
it's real. It's x
Yeah,
real,
yeah.
but this is
Only x, so you say h is not.
but for if you just think you're going to do the integrable system,
Yeah, yeah, of course.
well defined for
Everywhere. Yeah, yeah.
so if you find an eigenfunction which is not well defined for real values of each bar, this means that it's not an eigenfunction and you are missing something. And these are typically the limitations effect that you have to supply.
Yeah, but yeah, we thought a little bit about what it should be in the index, but yeah, we didn't come up with any answer basically there.
It means that you cannot get the exact eigenfunction.
Yeah, right, but we can get enough to compute index because that's our goal.
Other comments, questions? Okay, if not, we thank again.
Yeah, thank you.